Question 7 from nest 17, ninth question from the paper. This is also interesting, and I'll tell you why is it so. Okay, the value of the integral pi to 2 pi x squared plus 2 upon x cubed cos x dx is negative 5 upon 4 pi squared, negative 1 upon 4 pi squared, 1 upon 4 pi squared, 5 upon 4 pi squared. Now, because of the involvement of algebraic functions here, it is a bit discouraging to go for or to think about a plus b minus x property, or what you people call King's rule. Okay? Secondly, is it possible to eliminate some of these options? Okay, is it possible to eliminate some of these options, because two of them are negative and two of them are positive? So can we do that? Please pay attention that our integrand f of x, it is negative when x belongs to pi to 3 pi by 2, okay, and it is positive when x belongs to 3 pi by 2 to 2 pi. Okay, it belongs to pi to 3 pi by 2 and 3 pi by 2 to 2 pi for positive. Okay, now can you come up with a qualitative estimation as to whether the negative part will be greater in area or the positive part will be greater in area, or no such conclusion is possible? Qualitative, I'm not saying quantitative. Think about it. Did you get the question? The question is, from pi to 3 pi by 2, the graph of the function will be below x-axis because cos is negative in the third quadrant. From 3 pi by 2 to 2 pi, the whole graph will lie in the positive or the first quadrant, because cos is positive in 3 pi by 2 to 2 pi. So the graph of the function will be in the first quadrant. So what I'm saying is, suppose this is 3 pi by 2, suppose this is pi, and suppose this is 2 pi. I'm asking you to estimate whatever area you have here and whatever area you have here. Are they same or are they unequal in magnitude? Think about it. I think that without a grapher we cannot say anything to that. The reason being, we have that x cubed in the denominator. I mean, you can still come up with some estimation. If you split the denominator there, numerator there, it will be 1 upon x plus 2 upon x cube. 1 upon x plus 2 upon x cube. Now that still is not very much conclusive to decide whether this area will be greater or this area will be greater. You may be required to consider derivatives and decide whether increasing or decreasing, and you can do that stuff also. But coming back to the options, as it was possible for one of our previous questions where we just substituted a as 1 and got rid of some options, that's not definitely possible here. Okay? Now, according to me, this problem can only be solved if we use or employ a particular approach. Okay? And that particular approach involves observing the function or the integrand carefully and predicting what could possibly be the answer of the indefinite integral. Now here is what I mean. Suppose we take two rational functions. Okay, suppose we take two rational functions. Let us consider them p and q. I'm not writing x now. Now, tell me, if I take p into cos x plus q into sin x, and try to differentiate this, what will be the answer? P dash cos x minus P sin x plus Q dash sin x plus Q cos x. Or we can say P dash plus Q cos x plus negative P plus Q dash sin x. Raise your hands if you follow till this. Now this is which part? The difference?
So actually, I had a confusion.
Okay.
So you've written where x belongs to these two intervals.
No. That is we have stopped discussing that now because we were trying to eliminate A, B or C, D. If we could come up with whether this is greater than this. If that had been greater, then the answer would definitely be positive. But we haven't arrived at any definite conclusion for that. Okay. Maybe I should have written that there. Okay. So, although it is a definite integration problem with apparently no direct method of solving, so we have to either rely on properties, but if the properties are also not of much help because of the involvement of x squared and x cube, basically rational functions. So I'm asking you to consider a differentiation problem. I'm asking you to consider a differentiation problem where we have p cos x plus q sin x as our function to be differentiated, and it has given us a form p dash plus q cos x plus negative p plus q dash sin x. Now you might ask, why are we doing it? Okay, why are we doing it? The reason behind that is the fact that derivative of a rational function is always a rational. Say some other rational function. And derivative of sine cos, okay, they are essentially alternating their positions with, well, of course, change in the sign, but that is immaterial for us now. So if we take the product of an irrational function, of a rational function and cos, and for generality include the sign also, the derivative will also contain cos x into some rational function plus sin x into some rational function. Is it clear? Yes?
Yes.
Huh.
Yes.
Huh. Now there is one more thing which I actually forgot to tell you. If you observe these two functions, if you observe these two functions, 1 upon x and 2 by x cubed, notice that the derivative of this function is negative 1 upon x squared. Okay, the derivative of this function is negative 1 upon x squared, and if you integrate this function, if you integrate that function, then it would give you 2 into x raised to negative 2 upon negative 2. So this is actually negative 1 upon x squared because 2 will get cancelled. So 2 by x cubed is actually the second derivative of 1 upon x. Got it? 2 by x cubed is actually the second derivative of 1 upon x. Raise your hands if you understood this. Okay, in other words, derivative of first function, that is 1 upon x, is actually the integral of the second function, that is 2 by x cubed, and that seems to be matching or at least taking us forward in the direction that we are now aiming at. Meaning, if we now rewrite the result that we have got here, if we now rewrite the result that we have got here in other words, okay, I want to deliberately make that. So let's do it. So this is the result that we have obtained. But alternately, we could have also said that, okay, if derivative of this function is this, let's use this antiderivative part to arrive at the following conclusion. Please raise your hands if you understand this transformation or this step. Yes or no?
So can it be written?
Derivative of one function is other function. So integral of the other function will be the original function. Got it? Or no?
No problem.
Okay, fine. So now,
So are we trying to attack this question from the reverse way, reverse manner?
You could say that reverse. Yes, you could say that we are kind of doing it in that way. But again, I'll come to what I keep on telling you. See, in integration, there is no fixed strategy. Okay, if we try our usual ways, we fail miserably. We cannot proceed. Firstly, we tried eliminating the options, that also didn't work. Integration by parts or partial fractions is out of question because the derivatives will never vanish. I'm not sure about parts, but I'm very much almost sure that it won't work. There is no chance of substitution here. There is no chance of substitution. There is no chance of using the properties of definition. Okay, so some other way. Some other way. Although we did not discuss it in our first lecture, problem solving strategy, this could be one such problem solving strategy, especially for integral problems, where you assume the integral to be having a particular form. I hope you understood what I'm trying to say. I'm trying to say, if we assume that after integration we get a particular form, use it and then compare the coefficients. Okay, that's what we will do now. Okay, that's what we would do now. Look here. So we essentially want this, right? We essentially want this, and because of sin x being absent, we must say that negative p plus q dash equals 0, and p dash plus q equals x squared plus 2 by x cubed, or 1 upon x plus 2 by x cubed. Is it clear? We are basically comparing the coefficients. So cos x is there, so we made use of it. Sin x is not there, so we considered negative p plus q dash to be 0. Is it clear?
Yes.
Okay, so we now need to pick something here and see if that gives us the correct result. Okay, if that gives us the correct result. How can we do that? We can pick q as 1 upon x. If we pick q as 1, because if we take p dash as 1 upon x, then p will be log x, and we don't want that to take into consideration because log x doesn't appear here, right? Or there's no chance that a rational function will cancel log. Okay, so if we assume that q is 1 upon x, q dash will be negative 1 upon x squared. Okay, q dash will be negative 1 upon x squared. Then p dash would be 2 by x cubed. Okay, p dash would be 2 by x cubed, and what would then p be equal to? As we noted earlier, p will be negative 1 upon x squared. See, we have already noted this. We have noted that the first derivative of 1 upon x is negative 1 upon x squared, and second derivative of 1 upon x is 2 by x cubed. So that will now take us to the final solution. That is, starting with p dash plus q equal to 1 upon x plus 2 by x cubed, if we take q as 1 upon x and p dash as 2 by x cube, we can arrive at the conclusion that p is negative 1 upon x squared and the q dash is negative 1 upon x squared, and when they are subtracted from each other we get the correct result, or it matches with the integrand. Okay, it matches with the integrand. So whatever we had assumed has indeed given us the correct form. We require only PQ now. Therefore, this is equal to P negative 1 upon x squared cos x Q sin x 1 upon x sin x from 0 to not 0 pi to 2 pi. Forget about the second integral because the second part sin x is 0, sin pi is 0, sin 2 pi is 0. So all we have to do is we have to put first x as 2 pi, so cos 2 pi is 1, 4 pi squared is there, minus cos pi is negative 1 upon pi squared. So it now confirms that the answer is negative. Okay, 1 upon 4 pi squared plus 1 upon pi squared, 1 to 5 by 4. Do we have that option? Yes. Negative 5 upon 4 pi squared, that is option A. Okay, so let us write a note here for our reference. We can assume the integral indefinite to be of a form depending on integrand and then solve. So instead of integrating, we actually differentiated. Okay, instead of integrating, we actually differentiated. Okay, see here what we were trying to do. We were trying to decide whether integral is positive or negative, but we couldn't arrive at any conclusion. The functions prevented us from arriving. So we adopted that strategy. Got it? Have you followed it? Yes. Okay. So make sure to remember this also. Who knows, you might be required to do that in the exam.